Jupiter's moons are more dangerous than you think. Here is the truth nobody in the mainstream space community leads with. Jupiter has 95 known moons. 4 of them could kill a human being in ways we haven't fully mapped yet, and 2 of them are already killing our spacecraft. This isn't speculation, this isn't science fiction. This is documented, calculated, peer-reviewed danger. The kind that forces NASA engineers to redesign missions from scratch and then redesign them again. The kind that makes scientists stare at their data and quietly ask, what exactly are we sending humans into? Most people who click on a video about Jupiter's moons expect the wonder version, the isn't space amazing version. The version where Europa has a hidden ocean, and that's beautiful and exciting, and maybe there's life down there, and humanity's future is among the stars. That version is real, but it's incomplete. The complete version includes the radiation that would kill an unprotected astronaut in 15 minutes. It includes the volcanic moon that resurfaces itself so fast that any landing craft would be buried within hours. It includes the gravitational forces that tear spacecraft apart before they can establish orbit. And it includes the discovery so disturbing that NASA had to create an entirely new category of contamination protocol, not to protect us from the moons, but to protect the moons from us. Here's what nobody tells you up front. The greatest danger at Jupiter isn't what the moons do to humans. It's what humans might do to the moons. We'll get to exactly why that matters. But first, the threats that are already on the record. If you've made it 5 seconds into this video, you already know this isn't going to be a surface-level space documentary. Subscribe right now. Every week we go deeper than the headlines dare to go. Io is the most volcanically active body in the entire solar system. Not on Earth. Not in our region of space. In the entire solar system. It has over 400 active volcanoes. Some of them erupt continuously. The largest eruptions shoot material 300 miles into space. Io's surface temperature in volcanic regions reaches 3,000 degrees Fahrenheit. That's hotter than some stars. Here's what that means for any mission. In 1979, the Voyager 1 spacecraft flew past Io and discovered active volcanoes in real time. Scientists were stunned. They had predicted a dead, crater-covered world. Instead, they found something that looked freshly painted, because it was. Io's surface changes so rapidly that it essentially erases its own past. There are no impact craters on Io. Any crater that forms gets buried under new volcanic material within years. Let that sink in. A landing craft on Io wouldn't just face extreme heat and toxic sulfur dioxide. It would face a surface that is actively changing beneath it. Any equipment left on Io would be compromised within hours. Within days, it could be completely covered. The 1979 Voyager mission proved that any standard landing protocol developed for static bodies, the Moon, Mars, is useless on Io. Every assumption resets. But Io's volcano problem isn't even the most dangerous thing about the Jovian system. It's not even in the top 2. The most dangerous thing is invisible. Jupiter's radiation belt is not like anything else we've encountered in the solar system. Earth has radiation belts. The Van Allen belts. They're dangerous enough that early satellite missions had to be designed carefully to avoid extended exposure. Jupiter's radiation belts are 10,000 times more intense. Not 10 times. Not 100 times. 10,000 times. The charged particles trapped in Jupiter's magnetic field travel at nearly the speed of light. They penetrate metal. They penetrate shielding. They penetrate the electronics inside shielding. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, accumulated radiation damage continuously throughout its mission. Engineers designed it to withstand a total dose of 150 kilorads. By the end of its mission, it had absorbed radiation far beyond what its instruments could accurately measure. Here's the number that matters for humans. A lethal radiation dose for a human being is approximately 400 to 500 rems. A single pass through Jupiter's inner radiation belt would expose an unprotected human to approximately 36 rems per second. Do that math. An astronaut in that environment, without extreme shielding, would be dead in under 15 minutes. Not sick, not compromised. Dead. The current shielding technology we have for spacecraft cannot adequately protect human biology for the duration of a crewed mission to the Jovian system. This is not a funding problem. It is a physics problem. The shielding required would be so heavy it would make the mission architecturally impossible under current propulsion systems. NASA knows this. ESA knows this. They're not hiding it. It's in the mission feasibility documents. But it's rarely the headline. If what you just heard surprised you, hit that subscribe button. We cover the facts the press releases bury every single week. Europa is the moon everyone talks about, and for good reason. Beneath its icy shell, estimated between 10 and 30 miles thick, there is a liquid water ocean. Not ice, not permafrost. Liquid water. More liquid water than exists on all of Earth's surface combined. That ocean has been in contact with a rocky seafloor for potentially billions of years. On Earth, that combination, liquid water, rock, chemical energy, produces life. Every single time. Deep-sea hydrothermal vents on Earth support entire ecosystems that never see sunlight. They survive on chemical energy alone. Europa almost certainly has equivalent conditions. Here is where the danger enters. If Europa has life, even microbial, even simple, and we send a spacecraft there, we have to be absolutely certain that spacecraft carries zero biological contamination from Earth. Because if it does, we could introduce Earth organisms to an alien ocean. And if those organisms survive, if they compete with or displace whatever is already living there, we will have destroyed the most scientifically significant discovery in human history before we even confirmed it existed. This is called forward contamination. And NASA takes it so seriously that Europa missions must meet contamination standards stricter than any mission in history. The Europa Clipper mission, launched in October 2024, carries instruments sterilized to extraordinary standards. The spacecraft cannot orbit Europa directly because the radiation environment would destroy it. Instead, it will fly past Europa 49 times while staying in a less radiation-intense orbit around Jupiter. Think about that. Our best current spacecraft cannot orbit Europa. It has to visit in flybys. And during those flybys, it has approximately 25 minutes of close observation time per pass to fully investigate an ocean that might contain life. 25 minutes at a time. The radiation problem and the contamination problem are in direct conflict with each other. Here's why that matters. To protect spacecraft electronics from radiation, engineers use heavier shielding. Heavier shielding increases mass. Increased mass means less fuel efficiency. Less fuel efficiency shortens mission windows. Shorter mission windows mean less time for sterilization checks and biological contamination monitoring. Every solution creates a new problem. The engineers working on Europa missions aren't dealing with one challenge. They're dealing with a system of challenges where fixing one makes another worse. This is why mission planning for Europa has taken decades and cost billions of dollars before a single instrument has touched the European atmosphere. And Europa isn't even the most radiation-dangerous moon to approach. Ganymede is the largest moon in the solar system, larger than Mercury. It is also the only moon in the solar system with its own magnetosphere, its own internally generated magnetic field. That sounds protective. On Earth, our magnetosphere shields us from solar radiation. On Ganymede, it creates something different. Because Ganymede's magnetosphere exists inside Jupiter's massive magnetosphere, the interaction between the two creates narrow corridors of extreme radiation. These corridors are called auroral zones on Ganymede, and they are visible. Ganymede produces its own auroras, driven by this magnetic interaction. A spacecraft or human entering those corridors faces concentrated radiation exposure far exceeding the already extreme Jovian background levels. The ESA's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023. It is specifically designed to eventually orbit Ganymede. The spacecraft carries 150 kilograms of radiation shielding. That shielding accounts for a significant percentage of its total mass budget. And engineers still aren't certain the shielding is sufficient for extended Ganymede orbit. Comment below, which of Jupiter's moons do you think is the most dangerous? I want to see what you think before we get to the one that surprises everyone. And if you're learning something right now that you didn't know before, subscribe. This is what we do here. Most people who discuss Jupiter's moons treat the dangers as engineering problems with engineering solutions. That's the conventional narrative. Space is hard, but science finds a way. Radiation? Build better shielding. Contamination? Better sterilization protocols. Volcanism on Io? Design a heat-resistant lander. Here's the contrarian reality. Some of these aren't engineering problems. Some of them are physics constraints that cannot be engineered away under current or near-future technology. The radiation at Jupiter's inner moons isn't dangerous because we haven't built good enough shielding yet. It's dangerous because the shielding capable of protecting human biology for mission-length durations would require a mass that current propulsion cannot lift into the Jovian system economically or practically. This isn't pessimism. It's the conclusion that mission architects reach privately, consistently, and then frame optimistically in public press releases. The gap between what the press releases say and what the engineering documents say is where this story actually lives, and that gap has consequences. Here is the specific consequence nobody wants to say clearly. We cannot send humans to Europa, Io, or Ganymede within any currently planned mission timeline. Not because of budget. Not because of political will. Because of physics. The radiation environment would kill a crew before they could complete a surface mission. The volcanic environment on Io would destroy equipment before useful data could be gathered. The contamination protocols required for a Europa landing are so strict that no current robotic mission has been approved to land there at all, only to fly past. And yet, the public conversation about Jupiter's moons is almost entirely optimistic. Europa gets described as, quote, our best bet for finding alien life. Ganymede gets described as a future human outpost. Io gets described as the solar system's most dramatic geological laboratory. All of that is technically accurate. None of it captures the scale of the obstacles. If this is the first time you've heard the obstacles framed this honestly, subscribe. We don't do the sanitized version here. Callisto is the fourth of Jupiter's Galilean moons. And it is, quietly, the one that gives mission planners the most hope. Callisto orbits far enough from Jupiter to sit mostly outside the intense inner radiation belts. Its surface is ancient, cratered, and geologically dead. It has no active volcanism. It doesn't generate its own magnetic field to create radiation corridors. A crewed mission to Callisto is theoretically survivable, with near-future technology. Callisto has been identified in multiple NASA studies as a potential staging point, a base from which robotic missions could be deployed to Europa and Ganymede, while the human crew remains at a safe radiation distance. This is the plan that actually exists in serious mission architecture documents: humans at Callisto, robots at the dangerous moons. The irony is that the most scientifically interesting moons are the most deadly. And the safest moon is the least interesting. That's not a solvable problem. That's the Jovian system being exactly what it is. Here is the original conclusion that doesn't appear in any press release, any Wikipedia article, or any mainstream space news summary. The danger posed by Jupiter's moons isn't primarily physical. It's psychological. The real threat is the gap between how we talk about these moons and what we actually know about them. We talk about Europa's ocean as though it's a destination. It isn't, not yet. It's a target that has destroyed the expectations of every mission that's approached it, requiring constant redesign, constant scaling back, constant compromise between what scientists want and what physics allows. We talk about Io as though it's dramatic and exciting. It is. It's also a world that would actively kill any attempt to study it closely. Its drama is inseparable from its lethality. We talk about Ganymede as a future human base. It could be. Someday. With propulsion technology that doesn't exist yet, shielding materials that haven't been developed, and radiation medicine that hasn't been invented. The danger of Jupiter's moons isn't just radiation and volcanoes. It's the optimism that makes us underestimate them. Every serious mission to the Jovian system has arrived at Jupiter and discovered the environment was more extreme than pre-mission models predicted. Galileo, Voyager, Juno, every single one. The moons keep exceeding our worst estimates, and we keep adjusting our estimates downward while adjusting our public ambitions upward. That gap between the engineering reality and the public narrative is where the danger actually lives. And until that gap closes, every mission we send to Jupiter's moons will face threats we weren't fully prepared for. If you made it this far, first, share this video. Someone you know thinks space exploration is just a matter of building faster rockets. Show them this. And subscribe right now, because next week we're covering the Galileo spacecraft's final mission, How NASA deliberately crashed a $1.5 billion spacecraft into Jupiter to prevent it from contaminating Europa. The decision was controversial. The reasoning behind it will change how you think about space exploration permanently. Where does this leave us? Europa Clipper is in space right now. It will reach Jupiter in 2030. It will fly past Europa 49 times. It will measure the ice shell thickness. It will detect water plumes erupting from the surface. It will search for chemical signatures of habitability. It will not land. JUICE is also in space. It will arrive at Jupiter in 2031. It will eventually orbit Ganymede. Whether the shielding holds for the full mission duration is a question that won't be answered until it's already happened. On Io, there is no approved mission. Several proposals have been submitted. The radiation exposure during a close Io orbit exceeds what current spacecraft electronics can survive for meaningful data collection. We are sending our best technology to a place that is actively trying to destroy it, and the technology is barely winning, for now. The real lesson of Jupiter's moons isn't about the moons. It's about the assumption that we understand environments well enough to send things into them. We didn't understand Io's volcanism until Voyager flew past in 1979. We didn't understand the full intensity of Jupiter's radiation belts until Galileo spent 8 years absorbing punishment we hadn't calculated. We didn't understand Ganymede's internal magnetic field until we looked closely enough to find it. Every time we looked at the Jovian system with better instruments, we found it was more dangerous than we thought. There's no reason to believe that pattern has ended. The next mission will find something unexpected. The next mission always does. And whatever that something is, it will force another round of redesigns, another revision of what we thought we knew, another narrowing of what we can actually attempt. Jupiter's moons are more dangerous than you think. They're also more dangerous than we think. And the scientists who study them most closely are the ones who say that most quietly, most consistently, and most honestly. That's the video. If this gave you something to think about that you didn't have before, drop a comment. Tell me, do you think we should prioritize Europa exploration even at the contamination risk? Or do we wait until we can do it without any possibility of forward contamination? I read every single comment. Subscribe if you're not already. And I mean it when I say this channel goes places the mainstream space coverage won't. Next week's Galileo video is going to be one of the most unsettling things we've ever covered. See you there.